So yeah, welcome to this week's holograph seminar series. This week, Felix Haehl from the Institute of Advanced Studies in Princeton will talk about his recent paper together with Tarek Anous from Amsterdam. And in particular, the topic will be the p-spin glass model, a holographer's perspective. So thanks, Felix, for agreeing to give this talk. We are very much looking forward to it. And thanks for the audience showing up.
So thank you very much for the invitation. It's an interesting series. Yeah, Martin already said everything that's on this slide. So this is going to be about recent work with Tarek Anous. And so I should give you the disclaimer that my background is in ADS CFT and so on. So myself, I'm a little bit new to this subject. And but part of the point of this work and of this talk is to introduce this subject to the holography and the HepTH community and see if we can make progress in understanding certain phases of matter from the gravity point of view. I was also asked to give a lengthy introduction and review, so I'm going to start by reviewing certain things that will be relevant. And so the thing I got interested in this subject is because of, one of the reasons is that there were all these recent developments in low-dimensional holography that were very exciting, and many of them have to do something with the replica trick, if you wish. And the replica trick is one of the crucial ideas behind what I'm going to be talking about. Okay, so let me tell you about this interesting spin glass phase. And yeah, so the outline of my talk is going to be that I'll start with a review of the SYK model, which is perhaps more familiar to some of you, and some of the relevant phenomena that will play a role. And then I'm going to spend time introducing this p-spin model, and I'll tell you about replica symmetry breaking and the glass phase of this model. And I will put particular emphasis on features that are reminiscent of gravity. So for instance, there's going to be interesting limits where this model admits a conformal reparametrization symmetry that could then be related to a gravitational description. And as one signature of gravity, I'm going to discuss quantum chaos, which will be signified by 4-point functions. And in the end, I'll be more specific about what a holographic description might look like. There's also Tarek. Okay, so let me start with reminding you of certain features in this SYK model that might be more familiar, and I'll emphasize features that will be important and that we're gonna study in this other model and that are gonna serve as a signature of gravitational physics. So the SYK model is this disordered quantum mechanics of Majorana fermions, disordered meaning that these coupling constants J with some number of indices are drawn from a random ensemble. And this model has attracted a lot of attention because it's exactly solvable in the large end limit, and in particular at large beta J, which is the dimensionless coupling that plays a role that sets the energy scale in this model. Now, the solvability of this model has to do, or technically the way this is done is in terms of a mean field description, where you introduce some bilocal master field G and integrate out the fermions and express the physics in terms of this bilocal field. This effectively becomes a classical variable determined by some classical differential equation and becomes essentially solvable. So let me review some of the aspects that underlie the connection with gravity, which is most simply understood in this limit where beta J is large. So in this strong coupling limit, there's an effective description for this bilocal field G. There's an effective action, and it becomes approximately invariant under reparametrizations of time. So under arbitrary reparametrizations of tau. However, the So this conformal symmetry, this emergent conformal symmetry, is spontaneously broken when you consider the saddle point solution. So this conformal scaling solution with scaling exponent 1 over q breaks this general reparametrization symmetry to an SL2R symmetry. Furthermore, it's also explicitly broken, because if you consider now time reparametrizations around this saddle point, then because these are not quite a symmetry, they become soft modes whose excitation is caused in action. And this action is this famous Schwarzian action, which is also SL2R invariant, and describes the effective theory of those reparametrization pseudo-Goldstone modes. And this Schwarzian action makes the connection with gravity quite explicit, because it also appears as the boundary degree of freedom, or as the gravitational action describing the boundary degree of freedom of certain dilaton gravity in ADS2. Now, a complete, microscopic understanding of this holographic connection is still missing, but many features at low energies are described accurately by this JT gravity model. Another point to mention is that this symmetry breaking pattern also determines much of the thermodynamics and various dynamical questions and so on. So here's just one example, which is the entropy of the system. So you can compute the entropy at low temperatures, and you find some. Okay, so there's some extremal entropy S naught, which is which is not captured by this Schwarzian description, but then the Schwarzian description gives you a contribution to the entropy, which is extensive in n and linear in the temperature. So beta is 1 over t. And this property follows directly from the Schwarzian when you compute the free energy as the on-shell action and so on. Another way to think about this term is as the specific heat. So that being linear in temperature is, of course, a well-known consequence of conformal symmetry. Okay, so there are these thermodynamic properties. And finally, let me mention one more property of this theory, which you can understand from the Schwarzian action, which is a universal contribution to 4-point functions. And in particular, the 4-point functions that people have been interested in are these out-of-time order 4-point functions, which have to do with quantum chaos. So let me very briefly review that aspect as well. So the idea here is that you want to quantify quantum chaos, or the quantum butterfly effect, where the idea is always that you start at some time t, say here, and you evolve backwards in time, insert some small perturbation in the past, and evolve forwards again. And if the Hamiltonian evolution is very chaotic, then even a small local perturbation in the past disrupts the cancellation between the forward and backward evolution, and you end up with a very complicated operator here that commutes with almost no other operators, even if this perturbation here was very simple, local, and so on. So to determine, to quantify this property, to quantify how chaotic this time evolution is, one thing you can do is compare these two states. So you can compare what's the difference between inserting the operator at time 0 and at time t, or doing it the other way around. And it's clear that for very small times t, let's say the two operators commute, then these two states are roughly the same. So it shouldn't matter very much in which order you apply the operators. So that means they have large overlap. So if you compute this overlap between these two states, which is going to be our out-of-time order correlator, it's going to be large, or it's going to be approximately factorized. But now you can see that if you wait for some time, then these states do look very different, and their overlap goes to 0. And the faster this happens, the more chaotic the system is, roughly speaking. And this is this quantum butterfly effect, that the time-ordered and anti-time ordered states eventually have no overlap at all, even though they were essentially the same for early times. And as in the classical case, you can define a Lyapunov exponent, which quantifies this this notion of chaos, because the initial onset of the decay of this OTOC is indeed exponential, like here. Okay, so this is the interesting term we're interested in, which is the 1 over n suppressed contribution to the 4-point function that grows exponentially in time. And the Lyapunov exponent depends on the coupling, which is beta j in the SYK model. And of course, one reason the SYK model has attracted so much interest is because this saturates the chaos bound by Schenker-Stanford, and the Lyapunov exponent that you get from this enhanced Schwarzian contribution that I described before is the maximal possible. And this is going to be another signature of black hole physics that we'll discuss, because black holes have previously been identified as the fastest quantum information scramblers or thermalizers, so systems that saturate this bound. Okay, is that clear so far? Yeah, please just interrupt if anything is unclear. Now, in this talk, I will talk about the similar model, or a different model, which has some features that are similar to the SYK model, but it also has some interesting new features. And before I define the model in detail for you, let me tell you a few qualitative things to set up some of the intuition. So roughly what we're going to do is we're going to take this SYK model and replace the fermions by bosonic spins, sigma I. And we're going to have to constrain them to live on a sphere. So because they are bosons, you have to avoid runaway directions in the potential. And so you have to impose an additional constraint that these spins should lie on a sphere. And therefore, the model is going to have two-dimensionless couplings. Okay, there's going to be a beta j that's similar to the SYK case, and that's going to roughly describe the strength of thermal fluctuations in the system. And in addition, there's going to be another coupling that comes from setting the size of that sphere I mentioned. Okay, so the spins live on a sphere, and you have a choice how big you want to make that sphere. And this combination, this dimensionless combination MJ, is going to be a proxy for the strength of quantum fluctuations. So there's going to be interesting competition in this model between thermal and quantum fluctuations. And of course, the feature we're going to be mostly interested in is the fact that this model has a spin glass phase. So what is that phase? So what these models with quench disorder have in common is that you have this random potentials. So all these couplings between spins are randomly chosen from a Gaussian with a zero mean. So depending on the sign of these couplings, these spins want to point in different directions. And of course, that's too many constraints, and the system can't satisfy all these constraints, and it gets frustrated, meaning it has a hard time finding a minimum. So imagine some very complicated landscape of free energies, and so very rugged and with many local minima and spikes and so on. And the system tries to find the global minimum in this free energy landscape. But yeah, so it moves around in this landscape. But what happens in these spin glass models is that as you lower the temperature or increase the coupling strength, at some point there's a phase transition, and the dynamics suddenly slows down enormously, and the system becomes stuck in one of those minima. So the system becomes very viscous, relaxation times diverge, and the spins freeze in some state, which is locally stable, but it's probably not the lowest energy configuration. So you have a large number of metastable states, and it takes a long time to move between them. Another way to say it is that the system loses ergodicity, and the states become uncorrelated. So that sounds very complicated, and of course it is, but certain mean field methods allow us to make progress. Okay, so there exist certain more coarse-grained techniques or more coarse-grained order parameters that characterize this state of matter in a useful way. And a particularly important one is going to be this Edwards-Anderson order parameter, which you can think of as some sort of average self-overlap of these spins. So you see, you take the expectation values of all these spins and you have to square them before you average. The reason is that the local magnetizations, just the average of the one-point functions, that would vanish if you disorder average. So you have to square them to get something non-zero, and this quantity indeed can be non-zero. And if it is non-zero, that's going to characterize the spin glass phase. Okay, so it's essentially this quantity U that we're going to have all over the place is essentially a two-point quantity, which characterizes the fact that these different spins have this self-overlap. Okay, let me make this a little bit more concrete. Let me show you something more familiar where this quantity U shows up. So if you actually consider a true two-point function of these spins, and you disorder average it, it's this overline at fixed temperature, then you see different behavior as a function of this coupling MJ. Remember, that was the parameter that told us how strong are quantum fluctuations in the system. So this first situation here is where we are still far above the spin glass transition, and in that case, you have these. The system is very quantum in some sense. So as a consequence of that, you can see this oscillatory behavior in the two-point function that decays relatively fast. And now as you approach this phase transition to the spin glass phase, the dynamics slows down. Okay, so here in this situation, this is the two-point function as a function of time. As we get close to the transition, and now you can see that these different effects compete, and the decay becomes much slower, and eventually it becomes infinitely slow. And okay, it follows some interesting two-step behavior, but it's not going to be too important. But the point is that the dynamics slows down, and as you cross the transition, so in this third case, we're now actually in that other phase, in that spin glass phase, the dynamics in some sense freezes completely. So the correlator doesn't decay at all, but it approaches some asymptotic value, the two-point function. And this two-point function, of course, it's closely related to this order parameter. So it's clear that this asymptotic value is precisely this order parameter U. Okay, so that's perhaps quite a concrete way to see what this slow dynamics means. So the goals, some of the goals in this talk are going to be to characterize features of this spin glass phase, many of which I just mentioned, and extract universal properties, and then in particular also consider some of these more modern observables like this out-of-time order correlation function, which we know is a good signature to find signatures of gravitational physics, and see how these chaos characteristics interplay with this loss of ergodicity that you have in the glass phase. And of course, we're going to be interested in conformal symmetry, whether there's a notion of that emerges, similar to the SYK case. And then eventually, the question we would like to answer is, how do we think of all these features in the context of this ADS2 CFT1 paradigm where the symmetries are slightly broken? Okay, so that was the review and the overview. Are there questions so far? Okay, so let me now be more precise about what this model is that we're studying. So this was first written down in these papers down here. And so we have our bosonic variables sigma I that I mentioned. And we now write down a nonlinear sigma model for these guys. It's a sigma model because of this constraint that says that these spins are essentially the coordinates on a high dimensional sphere. Okay, so I'm going to refer to this as the spherical constraint that we implement here in this partition function using a Lagrange multiplier Z. Okay, so there's a Lagrange multiplier field which implements the constraint that these sigmas should lie on a sphere. And other than that, we have these disordered interactions that are similar to the SYK case. And we have a kinetic term which now has a tunable coefficient. Okay, so that gives rise to the dimensionless parameters that I mentioned, which characterize the different types of fluctuations in the system. Good. Now, the first goal, the first thing we need to do if we want to study thermodynamics or the effective large N theory is to compute an effective action or a free energy. And the tricky thing is that we, of course, need to compute the disorder averaged free energy. So we can take this Z from the previous slide. We need to compute log Z and then average over the disorder over the couplings with some probability distribution P, which is going to be a Gaussian. And the order in which we do these things is crucial. So it's important that we first take log Z and then we average. And of course, to compute log Z, one way to do that is to use this the replica trick. The replica trick, the starting point is to write log Z as this particular limit, and then say, well, we don't know how to compute log Z, but we know how to compute the powers of Z. Okay, so now all we have to compute is the disorder average of nth powers of Z. And to compute that, we simply introduce n copies of the system labeled by this index A, and we integrate over all the copies of these variables. Okay, so every spin and the Lagrange multiplier and all that, they now carry a replica index A, and we consider n copies of those. Now we proceed in a perhaps familiar way. So we introduce this bilocal variable, which also carries the replica indices. So this is going to be essentially a two-point function between the spins living on replica A and and replica B. And after we integrate out the disorder and the spins, so you do the usual tricks with these path integrals, and you obtain an effective action for this bilocal variable Q. In the SYK context, this was called G. That was the fermion two-point function I talked about before. Okay, so we obtain an effective action for this bilocal Q. And I didn't write the effective action here, but I wrote the Schwinger Dyson equation that you get from it. And it takes this form. So yeah, so okay, maybe I should note some features of this for those of you who are more familiar with the SYK model. So note that the off-diagonal components of this two-point function, they can now actually be non-zero. And that's because of the bosonic nature of this model. In SYK, these would have been fermions and these one-point functions would vanish. But because we are considering bosons, you can now get a non-zero value for these off-diagonal terms. Another point to be aware of is that the kinetic term here now has a coefficient m, which is a free parameter of the model. And finally, there's a Lagrange multiplier Z that shows up in this equation of motion. Okay, so how do we even begin solving such an equation? The basic ansatz goes back. Is this Parisi type ansatz for this matrix Q. Okay, so Q is our spin two-point function, and we make an ansatz now for the structure of that two-point function in replica space. So in these AB indices, and the idea is that you put a time-dependent two-point function QR along the diagonal of this matrix. So these are the correlations within a given replica. And then you add to it this replica symmetry breaking matrix that has this block diagonal structure. So the indices A, B run from 1 to n. So this is an n by n matrix. And we split it into m by m blocks along the diagonal, which have this constant value u in them. Okay, so along the diagonal of this matrix, you have these entries, which are subject to the boundary condition that q at time 0 should be 1. That's this spherical constraint. Now this is, so this is called one-step replica symmetry breaking ansatz. So you can do higher step replica symmetry breaking ansätze, where you refine the structure of this matrix and where you make these blocks more complicated and give them more substructure. Now, it turns out that in this model, this is not required, but that this ansatz is actually the most general thing that you need. So from that point of view, this is really one of the simplest models you can consider for spin glasses, because this replica symmetry breaking ansatz truncates, and all you need is this matrix structure. And furthermore, so the replica symmetry breaking refers to the fact that this matrix is not just a constant on every single entry, but that this U and this S are different. And in fact, the S, you can show that you can set that consistently to 0. So then the matrix just reduces to a block diagonal matrix, which has these order parameters along the blocks. Now, note that we have introduced new parameters into the game. In addition to this time-dependent two-point functions, we have now various constants that we're going to have to worry about. One of them is this U, the order parameter for the glass phase. Another parameter that we introduced is M, which is the size of these blocks. And we're going to have to figure out how to determine all these parameters. In principle, you can go and consider this Schwinger Dyson equation I had before. And it gives you equations of motion for these parameters, or at least for Q and for the order parameter U. To give you some idea, I wrote here what this equation looks like for just Q in Fourier space, where lambda is this self energy. Yeah, it's like a self energy that involves Q to the p minus 1. So it's like the sigma variable in SYK. And then in addition, you get some algebraic equations for these other parameters. So for the 0 mode of Q, because as you can see, this equation here is empty for k equals 0. So there's another equation that determines the 0 mode, and then there's an equation that determines U. What you don't get from this strategy is an equation for M. So how do you determine this M, the size of these blocks here? If replica symmetry is unbroken, so if we're outside of this glass phase, then M plays no role. But in the spin glass, we have to find a way to determine it. So perhaps the first idea one would have is to extremize the effective action with respect to that parameter to get another equation. Right, like the way you would get all these other equations. I'll sometimes refer to this as equilibrium spin glass, but I should say that this is going to turn out to be not quite the right thing to do. So in a few minutes, I'm going to tell you how to a different way to think about M, which does not satisfy this extremization condition. And at some high level, perhaps one can think of this as having to do with the fact that the essence of this glass phase is that the system does not reach equilibrium, or that it moves very slowly between these free energy states. And one manifestation of this is that we're not extremizing the action with respect to this parameter. But I'll get back to that in a few minutes. For now, let us understand a little bit a little bit better the phase structure of this model when you solve these equations. So the brute force way you can do that is just solve these equations numerically. So you can just put this on the computer and solve it. And then one thing you'll see is the phase structure of the model. And you'll find that, so I plotted here the phase structure as a function of temperature, or 1 over beta j and 1 over mj, the two couplings in the system. And everything up here, when both mj and beta j are small, is this paramagnetic phase where we're not in the spin glass, so where replica symmetry is preserved, and things are morally similar to what you may know from the SYK model. So in particular, this order parameter is 0, and the block size is just 1, if you wish. And then as you either lower the temperature or you increase the strength of quantum fluctuations, sorry, you decrease the strength of quantum fluctuations, this direction corresponds to decreasing the strength of quantum fluctuations, you cross this phase transition, and this order parameter u becomes non-zero, and replica symmetry is now broken, and the model has these glassy characteristics that I mentioned in the beginning. So, okay. Now let me describe a more analytic approach. So in particular, we're interested in the strong coupling regime and in the question whether there's a conformal and emergent reparametrization symmetry and signatures of gravity and so on. So let us ask if we can find a conformal limit. And the simplest place to look for that is in this paramagnetic solution. So up here, where replica symmetry is preserved, where you can indeed show that the equations of motion at strong coupling at low temperatures simplify. You can neglect certain terms, and the equations of motion take this simple form, which you can show is indeed invariant under reparametrizations. So this equation exhibits an emergent reparametrization symmetry. And similar to what I had in the introduction, this emergent symmetry is broken by the solution. So the solution to this equation is just this conformal scaling solution with a particular exponent that goes like 1 over p. P, I think I never said that. P is the order of the coupling. It's the number of indices that the J's have, these disordered couplings. And then the phenomenology of this solution is quite similar to the SYK case. There's a Schwarzian action and so on, which describes the soft reparametrizations. But then what we found is that this solution is actually unstable. So, it exists. You can write down the solution. It's analytically, it's all fine. But something deeper goes wrong with this solution if you actually consider the consequences of this conformal symmetry in a more dynamical setting. So one thing you can do, and this technique sort of goes back to this paper probably, is that you can consider this as a conformal field theory in some sense, and ask about the operators that can appear in the OPE of two of those spin operators, and they will be determined by the conformal symmetry. Okay, so I'm not going to go into detail, but you can just do that and take this conformal symmetry as a guiding principle to find the operators that can show up in this OPE. And what you find is a tower of allowed operator dimensions that you can get. So the first one you always get is this universal mode that has dimension 2. That is the analog of that's kind of analogous to the stress tensor. It's this enhanced contribution that is also described by the gravitational physics. And then on top of that, you find all these irrational operator dimensions that can occur in this OPE. So they take some values which are irrational and which are discretely spaced. But on top of all of that, you find one operator that has a complex dimension. And that's sort of the problem, that signals that this conformal field theory doesn't make sense, or that it's unstable because it has this complex dimension operator in it. Okay, so this conformal solution has this issue. And indeed, if you solve the equations numerically, you find that there's a different solution to these replica symmetric equations, which you can find numerically, but it has no conformal limit. It behaves very differently physically. So all the thermodynamics is very different for this solution, but that's the physical solution. Now, yeah, so the physical solution looks something like this. So this is constructed numerically, and you can see that this does not look like a conformal. This does not have the properties that you would expect from something with a conformal symmetry. So for instance, these on the left here, these are Euclidean two-point functions, but I'm also plotting the spectral functions for these solutions. Okay, so the spectral functions as a function of energy, frequency. And you can see that these typically have this kind of gap. So they have a lot of spectral density somewhere away from zero energy. So these solutions are quite gapped, and so you would not associate a conformal description with that. However, a feature that we'll get back to later is this interesting thing that what happens here, that as you increase mj, so as you go closer to the spin glass transition. So remember, this is all above the transition, but now we go closer to the transition. So the situation where the dynamics slowed down, and then we observe in this spectral function that the gap sort of gets smaller and closes. So some of the system becomes more gapless. So this motivates us to ask that perhaps after you cross the transition, perhaps there is actually a gapless solution, a conformal solution to these equations. Okay, so is there a conformal solution in the spin glass phase, and ideally a physical one that's not unstable? And the answer to that is yes. So that's the interesting solution I'm going to talk about now. Yeah, are there any questions? Okay, so just to recap, so I'm gonna now talk about the spin glass phase, so where the replica symmetry is broken and this order parameter u is not zero, and I'm gonna describe a conformal limit in that phase. So I'm going to describe the low temperature regime of that phase, and we're going to discover that there's a certain notion of an emergent reparametrization symmetry in the equations. And this equation, this solution is sort of going to be the main player for much of what follows. Okay, so yeah, so let's consider again these spin glass equations. Now again, it's strong coupling, so we take beta j large, and now we do another expansion. So u is now non-zero. Okay, so recall that along the diagonal of our two-point function matrix, the capital U, capital Q, we had these guys. So we had a split of the two-point functions into a constant, that was this order parameter, and then a time-dependent function on top of that constant. And in the strong coupling limit, in a particular strong coupling limit, deep in the spin glass phase, this QR is much less than U. So this diagonal part of the two-point function matrix is dominated by the constant U, and then it has on top of that these relatively small fluctuations. So we can do a perturbative expansion in that. And in particular, we can consider this self-energy lambda and expand it. So that's just one of this combination that shows up in the equation of motion. And we can just expand it for small QR compared to U. Okay, and when you do this expansion, you'll find equations. So this equation simplifies in a way that you can solve it analytically. So if you just keep the first order term in this expansion, you can solve the equation precisely and analytically, and you find some approximate solution, QR approx, to this leading order equation of motion. I wrote it here in frequency space, and gamma is some parameter that's it's like 1 over j roughly. So it's like a small parameter. Okay, let's understand some of the properties of this approximate solution. So there's an approximate analytical solution to the equations of motion deep in the spin glass phase. That's strong coupling. And so one thing we can do is look at the behavior of this solution at small and at large frequencies. In the low frequency limit, you can just expand this expression, and you find this, which has a 0 mode at leading order. And then at subleading order, it has this term that's like absolute value of the frequency. And this kind of term is associated with a scaling solution. If you Fourier transform that, it's like 1 over tau squared in the time domain. Okay, so this is like a scaling solution with conformal dimension 1. Okay, so this indicates that that this approximate solution becomes a scaling solution, a conformal solution in the low frequency regime. On top of that, in the high frequency regime, it is also well behaved. So if you expand the same expression for high frequencies, you get something that's finite. So what that means physically is that you can consistently impose this boundary condition, the spherical constraint that told us that the thing has to live on a sphere. The spins have to live on a sphere. That was this boundary condition, and we can consistently impose that at time 0 on this approximate solution because it's finite at high frequencies. So this approximate solution is well behaved both at long and at short distances. So that's kind of nice. So you see that in these plots. Here I plot the same approximate solution in the time domain in Euclidean time. The dotted lines are this approximate analytical solution. And you see that it behaves nicely both at short distances and at long distances here. So here's the conformal, where this is like the conformal regime. And here's the UV regime, where it's also finite. Or in terms of the spectral function, again, you can compare the analytical solution to the numerical exact solution in the spin glass, and you see that they match quite nicely. And for instance, that the spectrum is now gapless. You have excitations all the way down to 0 frequency, which is one of the manifestations of this conformal limit. All right, so now I'm going to get back to this value, to this M parameter. This M parameter was the object that in this Parisi ansatz, in this one-step replica symmetry breaking matrix 2-point function, that told us how big are the blocks, right? And as I said before, it's not the right thing to extremize the free energy with respect to M. And indeed, if we consider this approximate solution here, or the conformal limit of it, it determines M. So it comes with some value of M that you're not, you don't have to solve another equation for it. And the value you get does not extremize the free energy. So it does not satisfy the equation you would get from extremizing the effective action with respect to this parameter. So one way to think about this is that you can think of this M as some external thermodynamic quantity that's very much like a temperature. And like the temperature, you would then be allowed to tune this value to whatever value you wish that's required for the solution to exist. So a way to make this a bit more precise is to consider a thermodynamic ensemble where you have m physical copies of the system. Okay, so where m is not anymore part of the replica trick, but where you actually clone the system m times explicitly before you do the replica trick, and you consider this m as a free parameter in this ensemble, like the temperature. Then if you go through the same steps that we had before, you can compute the effective action and so on, you'll find that the effective action will just be proportional to this m. I guess that makes a lot of sense because you have considered m clones of the system. So the effective action is going to get an m up front. Now, if the m is a free parameter, you can do thermodynamics with this m. And there's one interesting quantity that you get if you compute the m derivative of the free energy, or of this grand canonical generalized free energy. Yeah, so this is called this complexity sigma. And if you compare with the usual thermodynamic quantities, where you take a temperature derivatives of F, you get the entropy. So what you get here, if you take this M derivative, you get something that's very much like an entropy in the sense that it counts states. But what it counts is the number of metastable states in this glass phase. You know, in this complicated free energy landscape, it gives you some counting of these metastable states. And it's also extensive in the number of degrees of freedom. So what I have here is some explicit expression that you find from an explicit calculation. This is sort of the complexity density, if you wish. So the actual complexity is again proportional to n. So, okay, I'm not sure if this is super illuminating if you're not familiar with it, but this is just to say that the value of m here plays a very important role, and there's a way to think about it in a thermodynamic sense, where this m is a free external parameter. And then the upshot that I want you to keep in mind is just the fact that there's an entropy-like quantity. It's called complexity, which is sort of which you get when you take the Legendre transform in this ensemble where you can vary m. Okay, and this entropy-like quantity adds to the entropy in some sense. Since it counts the metastable states in this interesting phase. So indeed the number of nearby states that you have in the system is indeed counted by the entropy density plus this complexity. And this expression here is precisely the complexity. That's because the entropy density itself is 0 to leading order. So the fact that we have an extensive number of nearby states in this model really comes from this complexity quantity. And that's we would like to interpret that as one of the signs of a gravitational description. The fact that even though this entropy itself vanishes at leading order, we still have an extensive number of states. And another sign is this reparameterization symmetry, the gapless spectrum, the things I mentioned before. So we see some signs that are probably reminiscent of a gravitational description. And now I want to consider one more quantity, which is this quantum Lyapunov exponent and the out-of-time order 4-point function, as another diagnostic of black hole-like physics. So let us now add to this list what we find for this quantum Lyapunov exponent. So that's what I'm going to describe next, unless there are questions. Okay, so let me briefly tell you how to do that. So you consider as we said in the beginning, the Lyapunov exponent comes from the exponential growth of the out of time of the 4-point function. So what we have to do first, or one way to approach this problem, is to first consider a Euclidean 4-point function in Euclidean time tau. And we'll be interested in the connected piece of it. The leading order, you get products of 2-point functions, and then you get some connected contribution. And this connected contribution is built recursively from ladder diagrams. So if you just consider the effective action and the types of interactions you have in the model, then you'll find that the leading contributions to this connected piece are these kind of diagrams, where our spins sit at the edges of the diagrams, and you add these rungs with p minus 2 copies of the 2-point function along to construct these kind of ladders. More formally, what you do is you compute a geometric series of this ladder kernel k tilde, and this k tilde is the thing that tells you what it means to add one more rung to the ladder. Yeah, okay. Now you can analytically continue to real time to compute the out of time order 4-point function that has this exponential growth in chaotic systems. Okay, so t is now real time, and we consider this configuration that in this complex time contour looks like this. And we simply analytically continue this geometric series that we saw in this Euclidean case. So there's some real-time kernel that tells you what it means to add more ladders to this particular real-time 4-point function. Now, we're not going to compute the 4-point function explicitly, but we just want to know what's the exponential growth. What's the Lyapunov exponent with which the connected piece of this grows? And the condition for exponential growth is that adding one more rung to these ladders does not change the final result. Okay, so adding one more k to this geometric series gives you the same result. Or in other words, the 4-point function should be an eigenfunction of this ladder kernel with eigenvalue 1. Where these integrals are like matrix multiplication. Okay, so you take this ladder kernel, act with it on the connected 4-point function, and you get back to connected 4-point function. And we have two ways of solving that problem. We can either do it perturbatively in this conformal limit using the approximate solution I described before. So in the strong coupling regime of the spin glass, we can do this perturbatively, or we can just take this equation and again solve it numerically. Let me very briefly, I guess, describe these two approaches. If you want to solve it analytically, I'm short on time. Let me just say, so you have this equation. So you want to solve this eigenvalue equation. The way you do that analytically is you make an ansatz for this 4-point function f, which exhibits exponential growth, where the Lyapunov exponent is a parameter in the ansatz that we need to determine. And now you consider this strong coupling limit where we have this approximate solution, the conformal approximation. And then you can solve, or you can write down this equation perturbatively. And what you find is that this eigenvalue equation reduces to a Schrdinger problem. Okay, just some second order differential equation with a particular potential. And this is a well-known Schrdinger problem whose spectrum of solutions is known. Right, so this on the right-hand side would be the energy in this Schrdinger problem language. And there's a discrete set of solutions to this problem. And there's precisely one that corresponds to a positive Lyapunov exponent here on the right-hand side. So the allowed values of energies for the Schrdinger problem correspond to allowed values of this Lyapunov exponent. And the unique one that gives you a positive exponent, so a growing solution, takes this form. So there's an analytical expression, which you can, for the Lyapunov exponent as a fraction of the maximal one. You can think of it in terms of this m parameter that characterizes the spin glass phase. You can also expand it at large beta J, so at small temperatures. And you see it's to leading order, it's linear in the temperature. You can also see it's proportional to p minus 2, meaning it vanishes for p equals 2. So the p equals 2 model, where the J couplings have only 2 indices, is not chaotic in this sense. And yeah, the most coarse-grained property of this is that these solutions vanish at strong coupling. If you take the temperature to 0, the Lyapunov exponent also goes to 0, but it's non-zero otherwise. So we do have a non-zero Lyapunov exponent in the spin glass in this frustrated phase. Here's a more complete plot for the numerical that you get from the numerics. So the plot I had on the previous slide corresponds to just the Lyapunov exponent in the spin glass. That would be down here. Yeah. So there's a lot going on in this plot. So what I show here is the Lyapunov exponent as a function of mj, the strength of the quantum fluctuations, and each curve corresponds to a fixed temperature, beta j. Okay, so we see the dependence of the Lyapunov exponent on these two couplings, beta j and mj. And so all the way over here, we're sort of far in the paramagnetic phase. We're far away from the spin glass transition, and the exponents eventually decay to 0. On this side here, past these dotted lines, we're in the spin glass phase, and we can see that the Lyapunov exponents are smaller, but they're still non-zero, interestingly. And they allow for an analytic approximation. And in between, we have these interesting peaks. So this is still above the spin glass transition. We see some other sort of transition in the Lyapunov exponents as a function of mj. And you can roughly associate that with these spectral properties I showed you before. To the right of this peak, that corresponds to the paramagnetic solutions that were very gapped, where we had the spectrum with a large gap and then some peak at some higher energies. And over here, we're still in the same phase, but this is where the gap in this paramagnet gets smaller and closes, and the dynamics slows down. And then there's some transition in between, which we can see as some local maximum in these Lyapunov exponents. So we can see from this plot this competition between the various couplings of the model. So it's quite a detailed characteristic, this Lyapunov exponent. Okay, now I'm out of time, so I'm gonna. I wonder if I maybe should just skip this and just say that because we don't have.
Let me remind you that you started 5 minutes late.
Yeah, it's true. Well, so the thing is, we don't have a story here anyway. It's just so these are just some speculations for what a gravitational description might look like. What I tried to argue in this talk is that we have some features in this model that remind us of gravity and that sort of suggest that there should exist such a description. So in particular, there was this emergent conformal symmetry and this marginal operator that described the scaling solution. And we had this extensive number of metastable states that's counted by this entropy-like quantity. It's called the complexity. We even saw that the quantum Lyapunov exponent is non-vanishing in the glass phase, even though it does vanish at strong coupling, it seems. So all these features are sort of reminiscent of what we know from this NADS2 and CFT1 paradigm, but everything is a little bit different, right? You have this conformal solution on top of some constant background value, and you have to introduce the complexity to account for replica symmetry breaking. And there's all these features that sort of don't quite fit into the paradigm as it's been studied so far. So the question is, what else do you need to make sense of this in gravity? And one suggestion is that this has this has to do with the ability of ADS2 to fragment. So there's a particular type of instability of ADS2 that's been known for quite some time. So this goes back to these papers. And you can think of this as follows. So you consider the most well-known way to get ADS2 in the first place is to consider extremal resonance from black holes in 4D Einstein-Maxwell theory and consider the near horizon region. And what was discovered in these papers and other works is that you can consider the multiple Reisner-Nordström black hole solutions in 4D Einstein-Maxwell. And there's different solutions which from far away look the same as far as the total charge is concerned. So you can have a solution that so I wrote an explicit solution here, which from far away, so for large x, looks like a solution with charge Q1 plus Q2. But as you zoom into the geometry and as you go closer to these parameters x1 and x2 that characterize this potential, you discover that there's actually two ADS2 throats carrying charges Q1 and Q2 respectively. Okay, so this solution has some free parameters like these charges and these parameters x1 and x2 where the different fragmented horizons sit. And you can construct more complicated solutions along the same lines to construct a whole moduli space of different geometries. And so the suggestion is that some features of this fragmentation picture of ADS2 of these solutions. So these are exact solutions. Are quite reminiscent of the features of the spin glass phase that I discussed. So the fact that you have this large moduli space of geometries, which locally minimize the free energy, and these are all stable solutions, and there are exponentially many of them. Now, the question is, can you somehow count them with some suitable notion of complexity, perhaps? And the idea would be that our order parameter u in this spin model is analogous to the dipole moment, to the electric dipole moment in these geometries, because the way you can distinguish this geometry from one that only has a single throat at infinity, the way you can distinguish them is by measuring the dipole moment or higher pole moments. So that is similar to the way we defined U before. All right, but I should really wrap up. So maybe I'll just leave this summary slide here. And thank you for your attention.
Yeah, thank you very much for a very nice talk. So are there questions? Okay, please. Go ahead.
Yeah, thanks for the great talk. So first, I have a technical confusion. So can you return to the slide where you define your O talk? So where exactly do you insert the rho beta factors? Is it two of them, or is it totally symmetric? Because I vaguely remember that actually the result depends on, here. So the result depends on where you insert the rows, and basically only one of these choices actually corresponds to the gravitational O-talk. So is that important in your case, or?
Yeah, it's not. I think it's not very important here. The configuration I chose here is this one, where the rho beta is split into two. Should probably be a trace instead of angle brackets. So the state is split in two, meaning on this contour we have beta half evolution here and beta half here. And the reason this choice is particularly nice is because the connected contribution is going to be real. So this thing here.
Okay.
is going to be real, or so the way it shows up in the kernel is here. There's this minus I beta half. That makes this one real. Otherwise, it's going to be complex, and you have to think a bit harder what you want to do. But at the end of the day, the Lyapunov exponent, I think, is does not depend on these choices.
Okay. And actually, I had another question. So, okay, you get a non-zero but non-maximal chaos exponent, not this Molde-Schenker-Stanford bound. So, okay, in gravity, so okay, this is probably obtained from this fragmented ADS2, but I thought that to get a non-maximal chaos exponent in gravity, you need to go, you need to have something else than the shock wave solutions. But wouldn't you still have shock wave in the vicinity of every ADS2 fragment? Or
yes, okay. So of course, I don't know how to reproduce this from gravity, but one thing to say is that everything on this plot here is at finite coupling. So in particular, these beta j's here, they're all finite. The most natural regime to compare with a gravitational description would be for a large beta j. Now, so one might ask what happens to these curves as we further increase beta j. So here, this beta j 3.14 is the largest that I plotted. But it's, you can ask what happens if you make this larger. And so the numerics gets more complicated as you do that. So I don't really have an answer for you. But roughly speaking, what we observe is this thing that I sketched here. Okay, so this is a schematic phase diagram, again, as a function of temperature and this other coupling. And these maxima in the Lyapunov exponents as a function of mj, they lie roughly here on some curve like this, above the spin glass transition. And they seem to approach this tricritical point here. So in other words, the Lyapunov exponent in the vertical direction is always the largest along this dotted line. And in the horizontal direction, it increases as you approach this tricritical point. And then the question is what happens as you go even further. So, so the gravity description would probably be the most appropriate somewhere here.
Yeah.
But it's hard to get there numerically, so I'm not sure. But I think what happens is that this line of locally maximal Lyapunov exponents continues under this transition, meaning you can't reach them anymore for smaller temperatures, but you get into the spin glass before you reach this maximal exponent.
Okay, so basically you lose this solution, which gives you this.
Yeah, or you cannot follow the solution beyond the transition.
Yeah. Okay.
Yeah. So one question I was wondering is, well, what's the maximal exponent that you can physically achieve anywhere here in this phase diagram?
But whatever it is, you're saying it's basically outside the applicability of the way we usually do it in gravity. It doesn't overlap with.
It's just no. So perhaps perhaps if we had a gravitational picture, perhaps it could illuminate how to think about this region here. It's not outside the applicability. It's just harder to do numerically. So the results I showed you.
I see.
Yeah.
Okay. Thanks.
The results I showed you, they went sort of not here, which is
clear.
They were more like here, roughly.
Thanks.
Okay, further questions? So let me jump ahead. So in this one-step replica symmetry breaking ansatz, you argued that you can set this S to 0. I really didn't get it. So did you also put it in and try to solve your Schwinger Dyson equation also with that and see that you can really self-consistently set it to 0, or what is the argument that you can set the S to 0?
That's right. Yeah, there's an equation for that, and you can self-consistently solve it. The equation is essentially proportional to S, so it's just you can just set it to 0 and it's consistent. But yeah, so when you start analyzing these equations, there's one more equation, which comes from which is about solving S, and you can self-consistently solve that by setting it to 0.
And my other question concerns one of your first slides, namely about if you are above this spin-glass transition. You said if it's non-gapped, you have this kind of two-step relaxation process. I'm just wondering how this time scale, where you go from the one relaxation time to the other one, like how this is, can this be computed, or how is that fixed? Which scale sets this competition between these two time scales?
So, right, roughly speaking, it should be mj, I guess. Yeah, so this refers to the fact that you first have this relatively fast decay, and then it goes over into some very slow exponential decay. And as you further increase mj, so there's some critical value for mj where you transition into the glass. And as you further increase mj towards that critical value, this exponential decay gets slower and slower. So,
and also this time scale where this change happens between these two behaviors. This also is pushed further to larger times, or it approximately stays the same.
So I think this time scale here, where this transition happens, is like some order 1, or some time of order beta. Well, yeah, I think so. So as you can see in this third plot in the spin glass case, you still have some similar scale here, which is still at the same place.
So this is for fixed beta times j, I guess.
This is for fixed temperature, yes. Yeah.
So can this order 1 number then scale with beta times j, or it's not clear?
Yeah, I think it moves with beta j. Yeah, I have to say I don't recall how it scales with beta j, or if there's an analytic relation. It's going to depend on it a little bit, but.
Okay, further questions.
Yeah. But so everything happened. The case where you have a spin glass transition at fixed beta j is anyway just some range of beta j, or at least where this transition is second order. So it's not like you can take beta j to be some crazy large or small value, but it's just some relatively small window.
Okay, further questions?
Can I ask a question, Martin?
Of course, go ahead.
Okay, thanks for the very nice talk, Felix. My question is about simple generalization of your model to 1+1 dimension. And I would like to understand, do we intuitively, do we have to expect to observe some non-trivial feature in the diffusion process or the value of butterfly velocity in the spin glass phase in your model?
In 1+1 dimensions?
Yes.
Yeah, I don't know. Well, that, of course, that would be interesting. So what would be the model? Like a chain of this one or something?
Yes.
Yeah, one could probably go and study the p-spin chain. Above the transition, I would expect that it's kind of qualitatively similar to the SYK chain.
Okay, yes, yes.
Below the transition, yeah, I don't know. I mean, that would be interesting to study.
Thank you. Thanks.
Okay, further questions? So then let's first stop the recording. No, first let's thank Felix again for this nice talk. Then stop recording.